like this one. This one's a rate. It says make and justify as many statements as you can. So as a group, you'll be making as many statements as you can about the truck's speed at various times. Then lastly, number 3, if you have time, it tells you to look back at your work and that your answers should or maybe not, right? Whatever you did, relate to the geometry of each graph. And I'll leave it up to you all to just go ahead and read the 4 instances down here. All right, I'm gonna go ahead and give you all 8 minutes of time to work on this. So again, individually process this before we jump into our groups. I'm gonna start the timer and feel free to ask me questions. Don't ask me questions about how to do it because that's what you'll be doing in your groups. You'll be figuring that out. But any other clarifying questions about what we're doing right now, feel free to use the chat. Just giving some wait time.
And we're just supposed to like jot down ideas on it, right?
Yeah, ideas, and try your best as a group to try to come up with an answer to the best that you can.
Okay.
Do we have to turn this in?
Basically the turning in of it is I have access to the slides, so I'm able to just access it. Like whoever did what, I'm able to see it. So you don't have to turn it in, if that makes sense, because I already have it. Great questions, everybody.
Sophia, you're sharing your screen, right?
Mm-hmm.
And then
We just joined the slide.
Yeah. So this, yeah, sure. So that's the image and then the slides. So right now, what we have to do is we have to talk about what we saw on the graphs. Viviana, can you go first?
Sure. I was kind of confused by the graphs, to be honest. Because they're supposed to be, oh wait. Oh, we're looking at the freeway fatalities one?
Or I think it's the same graph, it just doesn't have all like the long paragraphs before it.
Oh, okay. Because I thought it was two separate graphs.
I think, actually, Mr. Dono, is it both graphs or just which one?
Both graphs as in that you're supposed to do, or as in both graphs like are related.
Like as in when we create this poster, is it about the first or second graph? Or
So
both?
there's 3 questions on it. Number 1's question is find the distance the trucks traveled, which is the first graph. The second problem is about a different graph, which if you scroll down, you'll see. Now that's a different truck. And this one is giving you distance, and you're trying to write down all that you can about its speed at various times.
So is for the poster, did we talk about all 3 questions then?
That's correct. And if you don't get to number 3, it's okay. I think as long as we get to 1 and 2, that's all right.
Is there a way that we can see the 3 questions again that you showed us earlier?
If we go ahead and maybe whoever's projecting, if you go to the slides that you're supposed to create your poster on. Yeah, and if you go to the first slide, you have the questions.
It's because what's the x-axis? That's the hours?
Yeah.
You said 6?
But like from 6 to these 20 to the first dot is 25 minutes. I mean, not 25. Is it? Yeah, 25. And then this would be the first 25 minutes. Oh shoot. This right here, this little curve, and it looks like it doesn't look all the way equal, these 2 sides, but I guess we could like divide it by 2, and then we would get 30 miles per 25 for these 25 minutes.
Okay, so you said
sorry. I think that was like 30 miles per hour, but that's not like the amount it went for that certain time. Like from 6 to 7, we had to find like how fast it was going, not how long it went for. I don't know if you understood that. Like, is it saying
That's why
the total?
after we find that it was going for these 25 minutes, it was going for only for it was going 30 miles. That means it went. Oh, you're right. Man, I don't know, man. This is hard.
Also, I also wonder because there's a lot of pointings and stuff like
Can't
of
hear you, Mr. Martin.
explanations. I was just wondering like if it would help because I saw a lot of like pointing to the graphs. Whoever, I think that was Edgar doing that, and then James, you were like kind of saying like, oh wait, if it helps to already put this on a PDF and start marking it, that way you can just have something to plop in your slide.
Miles per hour decrease.
10-mile decrease.
10-mile?
Yeah.
Sorry. Okay.
Hold on, I'm sorry.
This is what we beat Kit, JK. Just kidding. What? Oh my god, teacher's right here.
Okay.
Oh, and then okay, well, she's not here, but he's right, write this down. And
Okay,
then
I'm back.
from what seems to be from 8:40, well, if we're gonna be correct, from 8:40 to 9, the vehicle had seemed to stop because then it went back to 0.
Yeah. Yeah.
So from 8:40 to 9, the car seems to stop.
Yeah, to 9.
Who got some stuff done. Some groups who didn't get to yet, but if you can please just jot down what you at least talked about in your slides, like for example, group 2 and group 3, that'd be great because I heard conversations happening, but not all of it was getting down into the slide. I definitely want all your ideas on there. But I definitely kind of want to hear about group number 4. You all got some stuff down. Kind of like if the reporter of that group or anyone in the group, if y'all can please kind of share what's happening here on your graph. Let's see, we have something in the chat. No, Sophia got kicked out. I don't know how that happened. Tell her to rejoin, but we're in our last minutes. That's okay. So group number 4, the reporter/recorder, if y'all can share with us and unmute, or anyone from that group. So for this one, Sophia, Juan, Viviana, or Shania, if y'all can go ahead and explain what's happening.
Yeah, I'll go since Juan is typing.
Great.
So, did you want us to talk about the first one or the second one?
Let's do the first and then second would be great.
Okay, so the first one, we're all kind of confused, but Sophia had the idea to like kind of break it down into shapes so we could just get like the area of that shape. So we did it from like a little past the 6 to a little past the 8, and we realized that like the points in between each represent 20 minutes. So that's why the 0.2 is down there. And then we would just like multiply it by wherever it would go up in the speed.
Question, how did you know to do the area? What is, like, I want to know about a little bit more about that. How did your group know that to find the distance you needed the area?
That was Sophia's idea because we didn't know what to do, and she had kind of already started it. So.
Oh, and then if Sophia not here?
Yeah.
Sophia,
I think we did something like this last year, or like you had told us of a formula where the distance is equal to the speed times the time.
so that's related to that. So distance equals speed times time. And then, okay, and then kind of connecting that to areas. And I wish I could hear, and I think it was, and that this was the correct Sophia, right, that worked in this group. Yeah, okay. Cool, let's quickly hear about number 2. Who can tell me about number 2 from this group?
I can tell you about number 2.
Yes.
So for number 2, we thought it was a little easier to decipher because it was kind of just speaking on the, like, the distance like traveled in like the time. So when we were doing it, we were like, oh, if you look from 8 to 9, right, it's traveling at about 50 miles per hour, and then after that it starts to kind of have a consistent travel time. So if you look at like 9 to 11, it's pretty consistent and it just kind of stays the same. So it was traveling the same speed over that time. Like it was, the traveling the same distance. So it's like always the same distance there. And so we were just kind of talking about how the distance in the second one is kind of more consistent and it's easier to figure out. And that's what we're just kind of breaking it down to see if we could figure it out more like concisely.
And clarifying question for me is, how did you know that the speed is about 50 from 8 to 9? How did you know that?
Well, I just realized that was an hour, and if in 1 hour they had traveled 50 miles, and I'm like, and then it must be 50 miles per hour, or it could be something more like deeper, but we didn't get past that because we spent a lot of time trying to figure out the first one because we thought it was more complex.
Okay. And if anyone wants to jump in there about like, if they have a deeper idea onto why the first hour is 50 miles per hour, maybe related to the shape or what's going on in the graph, feel free to jump on in.
Can use the formula too, I think, because if distance is equal to speed times time, then you can make it so that speed is equal to distance divided by time.
Ooh, and distance divided by time in this particular graph is called what in math? Usually we call it something. If no one knows, that's okay. Like this right here is 50. This line right here. I hope y'all can see my mouth. Sorry, my mouse. So yes, it is related to the distance over time formula for sure. But what else does this graph have? It's another word.
All right, angle.
Angle. What's another way to say angle in math? Kind of like, it's like an angle.
Trig. I don't know.
Well, trig.
A
It
degree.
starts with an S, y'all. Starts with an S.
Slope.
So yes,
that's because if you multiply 5 times the 18 seconds that they travel, that's 90 meters that Fritos travel. And looking at the flip side, if Frito travels 90 meters in 18 seconds, you can do the exact same thing, and you can find that every second she traveled 5. In Frito's graph, they traveled 5 meters. That's 90 as well. So they both have sort of the same endpoint. You just have to use math to find it. It's kind of like what we did with one of the first things we did, like the breakout rooms for the first day, where we had to find like the total distance traveled. You kind of just figure out how much they're traveling for every second and then multiply that times what they're traveling. And that's basically how they prove each other. Does anybody else have any ideas? That's what I got for that.
That makes like perfect sense. So
I think the homework that we were supposed to do really helped understand this too. Because when I did it, I kind of created my own graphs and try to use them to explain it. But this is basically what, like, if you haven't even done the homework yet, I'd probably suggest doing things like this. That way you can really explain it. Because then it's like, this is 90 and this is 90. They both end at the same time. That means they're equal, because I'm sharing, I think I'll just be the one.
What else? What do you guys like? Okay, wait. What else do you guys think we should add?
I can tell you why the bottom graph confirms the top one.
Yeah.
Okay.
Bless you.
Thank you. Thank you.
If you take the 5 and multiply it by the 18, you get 90. And then when you look at the top graph, you end at 90 on 18 seconds. So then it like the bottom one confirms the distance for the top one.
Okay.
The top.
Okay, we see. Okay, so let's say we see lot. What did you say? You said
It's
that both graphs were consistent.
Yeah.
Okay. Are consistent.
Yeah, are consistent.
You can say how for Frito's graph, the slope is the same throughout the whole. Actually, I don't know.
Yeah. Also, you could say, yeah, Fritos,
So Frito's graph,
or you mean slope,
or
or
the graph has the same slope throughout. Has the same.
yeah, they or both graphs. You could just say both graphs have the same. Both have the same slope.
But Frito's is just like straight across though, so I don't think it even has.
Okay, so then just put. But then how would that show that they're the same?
Oh, you're right.
You could say that they both end at 18 seconds.
Both and 18 seconds, you said?
Yeah.
What else can we put? Kaylin or Evie, do you guys have anything? I don't know what else we can put, to be honest. Both graphs are consistent. Both graphs end at 18 seconds. I don't know.
And I'm not exactly sure what this group decided on for this one here, but we're in agreement. So yeah, the second one is going to represent the rate. The first one represents position. Awesome. And now confirming it, I noticed we see some math here. For example, they did 18 times 5, you get 90. So the 18 at the bottom right here times the 5, like you're doing the base times height, which is kind of like finding the area of this square right here. It gives you the 90, which is the total distance. Now let's see if there's any ones that kind of show how this right here, the one on the left-hand side, verifies Frida's graph. So let's see. Right here, awesome. I see rise over run. So the slope of this graph is 5, which gives you the rate. So this one, like instead of kind of like typing out their explanation, I could see it with the way they annotated their graph. So they're saying basically the slope of the distance graph gives you the rate, which is basically her velocity graph or her speed graph, whatever it is you want to call that second one. Perfect. And then this one confirms this one because they did 18 times 5 is 90. So they visually showed that here. This group at the end, mostly like they have that visual as well, but it's like kind of explained and typed out here. They're showing the same thing that kind of this group over here did with group number 1 here. Awesome, y'all. Great, so go ahead and take a look and process that, and I'm gonna go ahead and bring us back together to synthesize this. So in some groups, I think some groups that I popped into were like, this totally reminds me of that first group activity we did with the graphs and the truck. So yeah, it's definitely related to that. So let me go ahead and bring us back to our slide. It is, and it's gonna be driving our unit. It's actually gonna come up again when we do our summative task, which is the mini final. That will be coming up the end of this week and also a little bit of next week, which is going to be the end of our module. But just a few reminders, and we did write this down in our notes, but remember the total area under a speed graph or any rate graph approximates total distance because we know that rate times time equals the accumulated unit. For example, it could be meters per second times second equals total meters, or it could be miles per hour times hour equals total miles. Rate times time gives you the accumulated unit. It's a big idea. And a lot of you applied that big idea in this group activity because you were doing that multiplication. You can determine the speed or rate from a distance graph by looking at the slope. So I noticed how that first and the last group looked at the slope and they were able to determine the rates. Like, oh, the slope is 5. That means the rate is 5. So she was going at 5. meters per second. So that's how you determine the speed, rate, or velocity, right? From a distance graph or a position graph if you look at the slope. So that's that second big idea. And then the third big idea, we didn't really use it here. It will come up in our, you know, our summative, our mini final, but of course you could determine when an object stops in a rate graph or a distance graph. And if you look at the Khan Academy videos, right, if you haven't yet, please make sure you do that. Let me know if you do do it so I could give you credit for it. But if you looked at that, you could tell even more information. You can even tell when an object stops, turns around, changes directions, and so forth. So there's a lot more information you could tell from motion graphs. But this is just a great synthesis of the two main big ideas. We talked, we refreshed about the derivative, and we talked about the different meanings of the derivative, like how it represents the slope of a function, how it gives us, you could visually see it as a tangent line to a curve. I also reviewed with you that power rule where you bring down the exponent, multiply, so forth. That's how you take the derivative. And then I also review with you how y'all used it in a past mini final. So we refreshed on what the derivative was. The next thing we did last time was we talked about this essential question that's going to drive this whole unit. The fact that the area under a rate graph, so if I was to shade this area here, right, the area would be 50 times 3, which is equivalent to my total distance. But we also saw that if I take the slope of this line right here, that gives me my rate. So there's like a weird cyclical nature happening, or a weird connection between a rate graph and what we call on the right an accumulation graph. So there is this cyclical nature, and we're going to be studying this, and it's going to drive us this unit. So that's something we talked about last time, and I'm going to keep kind of bringing up this image up so we could make those connections in our brains. Last but not least, we ended class last time figuring out what an antiderivative was, and how we kind of introduced this as I had you all think about, well, what can be replacing the red question mark? And basically kind of with trial and error, we were able to figure out that the derivative of x, the derivative of x squared gives me 2x. And this question mark is basically your antiderivative. For this one, it took us a little bit more practice, but I believe we got this as our antiderivative, 1.5 x squared. And how you test that out, like testing if your antiderivative is indeed your antiderivative, is you check it by taking the derivative of your antiderivative. So what I mean by that is you bring this 2 down, subtract by 1. Oops. Sorry, we got Shannon coming. That's why my marker went away. You get this, which is of course equivalent to just 2x, so checkmate. This one, when you check it, bring down the 2. 2 times 1.5 is indeed 3. And then 2 minus 1 is just 1, which indeed gets you this. So you can check your antiderivative to make sure it does give you an answer to the derivative, if that makes sense. So we kind of talked a little bit about this last week. We're going to go ahead and finish up our discussion on antiderivatives and also get a rule so that you can easily find the antiderivative of any function with a power. So that was our little recap. Let me know if anyone has questions on that recap. Okay, and if there's no questions on recap, let's go on to continue our talk on the antiderivative. We are on slide 5, everyone. So the antiderivative, our learning target will continue to be, I can investigate and define the antiderivative. Again, I don't know, I keep adding a little dash there, but I believe you can write it without the dash. I've seen it both ways, but you know, you might see it written like this or together like you see in the title. But here's our learning target. Let's go ahead and read that, make sure we prepare ourselves for this learning target. So again, we're coming in with an open mind. We're going to be investigating the antiderivative, and then we're going to be preparing to actually define what it is and actually get a little shortcut as well. Okay, so first thing that I'm going to show you is this. We're going to be having a Padlet check though, after we get a little bit of investigation. We're doing this investigation actually as a whole class. It's not like a groups thing, not today, but right now this is as a whole class. Let me first actually have you take a look at any patterns you might see here. So what I have for you are in this table, let me just color it. This right here is a function. So I just wrote down common functions, common power functions. Like basically you have your constant 1, you have your x squared function, you have your x cubed or x to the 3rd function, and then you have your x to the 4th. Then what I did is I included another table where I put what the antiderivative of the function was. And I wanted to see if y'all can notice any patterns that you could hold on to, and then kind of put whatever pattern you see once our Padlet comes up. But just for the moment, just go ahead and take a look at this table, process any patterns you might see. And then we're gonna synthesize that. Okay, and we already, there's a notice of a pattern that's already here in the chat. Let me write it out here so y'all can see that. But you could also put this on the Padlet once it's time, but I just want to write it. The root is always 1 more in the antiderivative is something that was mentioned there privately in the chat as a kind of like a little notice about the pattern here. So I definitely see the 1 more that we're talking about. Like this is 2 and then it's 3, 3. 4, 4, so it's always 1 more, and the antiderivative was something that was noticed right here. Cool, cool. But for the moment, everyone else, go ahead and just take a look. I'll pause here. We started talking about it. Let me go ahead and give everyone the Padlet. It's also on slide number 8 if you're there with us. So something that was new, and by the way, if you're still adding your comment, please do. You can still write in your comment there. Something that was new, as a new thing that came up here, was I think the antiderivative is sort of like a reflection of derivatives. It's basically the same point, but like shifted, like vertically or horizontally. It seems like a fraction or some portion of the original derivative. The next one, a lot of you mentioned patterns. So it follows a pattern, maybe based on the derivative, was something that was mentioned. And again, I highlighted this because that was mentioned more than once. So also seeing patterns. The mention of the root is always 1 more in the antiderivative. That was the pattern that was noticed earlier. Then here was a new idea about what the antiderivative is. It's going to show us info that's different from the derivative, but it's also relevant and related. That's interesting. And then we have here another new idea. I think the antiderivative is the outcome graph of an OG function. And I see that reflection of derivative coming up. It did come up. Let me go back up because I saw something new happening right here in Shannon's comment. So I see that the antiderivative rule is this. So there's this rule or the pattern that's happening. I know it makes sense. And then there's some further thoughts. I'm going to highlight this too because this is new. But let's go ahead and have some information now. After our little investigations, the antiderivative. First thing. So the antiderivative is actually exactly what it sounds like. The antiderivative is the reverse of the derivative. That's exactly what we're doing when we're doing an antiderivative. Let's talk about some examples. So the derivative of x squared, if you do the power rule, is 2x. So we know that first part from prior modules. The derivative of x squared is 2x. Bring down the power, subtract 1. That means the antiderivative. So if I were to go backwards, reverse, right? That means that the antiderivative of 2x is x squared. So that's how we're kind of using the language. So if I go backwards, that is my antiderivative. I'm just going to put antider. Hope y'all know what my little annotation means. I could not write down the whole word. So that's just a little example, right? Next. what if we consider the derivative of x squared plus 2? Well, we know if we were to follow the regular derivative rules, right? You bring down the power and subtract by 1. You would get 2x to the first power. But then first power is just written as x. So I don't have to write to the first power. You would just get 2x. And then the derivative of a constant is 0 by definition. So then we have 2x plus 0, which is simply also 2x. So we have the derivative of this other function, x squared plus 2, is also just 2x. So then the antiderivative of 2x is also x squared plus 2 and x squared. Do you all see how the antiderivative of 2x has more than one thing? It's this and also this. And I bet you could come up with even more antiderivatives of 2x, right? So what the main point is here is that the antiderivative isn't unique. You can actually find a lot of antiderivatives for one function, actually. So we're going to be generalizing this as a rule later. So I don't know if y'all remember Shannon's comment when we saw the palette, that there was a plus C. That's the generalization that we're talking about. But we're going to see that soon in a second. Does anyone have any questions so far about this slide, number 9? About antiderivatives and kind of finding out that you can have more than one antiderivative for many different functions. All right, if a question pops up, feel free, and I'm happy to go back and address it. So let's move on from slide 9 and let's transition to slide 10, y'all. Dun-dun-dun, there's the rule, y'all. The antiderivative power rule. Now, I know as you're looking at this, there's kind of some new notation, right? There's this symbol. Does anyone remember what this is called? Probably, I don't know if y'all remember or not, but there is a new symbol. New symbol as far as calculus right now. Yep, you have a new symbol. You also have this dx happening right here. Dx, we'll just put question mark. What is that? But basically what this formula is telling us is if you want to find the antiderivative of some x to the nth power, here's the rule. And some of you notice the fact that in the antiderivative, you were adding by 1 or increasing by 1. Y'all remember that's that portion right here that you see. You're increasing by 1 and you also have that division, the 1 over blah, that's right here. That represents the same thing. This plus c is the generalization I was talking about because there's more than one antiderivative for one function. In order to encompass all of them, you have to add plus c at the end of it. This is the rule, and we're going to get some practice in the next slide on how to use this rule. That way we don't have to guess and check no more. Again, for now, this symbol, let's go ahead and treat it as it representing find the antiderivative of. So let's just take this new symbol to be find the antiderivative for now. Antiderivative. Later, we're going to know a little bit more deeper about what this symbol represents really. But for now, let's just look at it as representing, telling us to kind of take the antiderivative of something. I'll pause here on this rule. Let's see if there's questions. I added in a little note there for that plus c. Again, the reason there's plus c in the rule is, again, because there's more than just one antiderivative for a function. So I want to make sure that's, if you're making some annotations on your slide, do make sure you include that if you are curious about the plus c in the rule. Plus c basically represents plus constant. C could be any constant. It's kind of like a little placeholder. Okay, let's go ahead and just put this rule into practice. So let's do this. Let's find some antiderivatives. Oh, goodness. Let's see. So I'm going to write the rule somewhere on my page right now. I'm just going to put it right here. So if I have some x to the n, I know that the antiderivative is going to be x to the n plus 1. And then I'm going to divide it by n plus 1. And then I have to put plus c at the end of it. I'm going to just shorthand this. So the antiderivative of something, here's the rule. And I know there was a little dx in the formula, but there we go. Okay, so now I'm looking at this. Okay, so first off, it has to be in this format where it's x to the nth power. So the 2 I'm going to kind of just disregard for the moment. I know that x is also known as x to the first power. So here's my power. Now I'm going to take the antiderivative of the variable while just at the moment ignoring that 2 in the front. So the antiderivative of x to the 1 is simply going to be x to the 1 plus 1 divided by 1 plus 1. Let's do it. I'm just applying that rule straight up. Divided by 1 plus 1. And I can't forget about my plus c. Now, once I've taken this antiderivative, I'm going to go ahead and bring my 2 down in front like this. Now all we have to do is simplify it. 1 plus 1 is 2. So I'm going to rewrite this as 2 divided by 2 plus c. Now, I have this expression written like this, and I'm going to ask you all, is there any way I could kind of simplify anything that's here? Let's see if anyone has any ideas in the chat. Like I mean, I wouldn't mark you wrong if you wrote your antiderivative like that. It's correct, but we could simplify it. Then we have the 2. Yes, that 2 that you all see there. Thank you, Edgar. Let me change my color. 1 second. Let me get out of the chat. Okay, there we go. So y'all see this 2 and the 2? Basically, this is like 2 divided by 2, which is 1. You can cancel this out. And then, therefore, our antiderivative in simplified form is simply going to be x squared plus c. That is the antiderivative of 2x. It's x squared plus c, and c represents any constant. And again, I know I was addressing, I still remember your question, and this is Sophia P's question, when you asked, what about the constant? That's how we take care of it, is adding the plus c. And I'm bringing back this question. We're gonna, soon, everyone, we're gonna be jumping into a Padlet, but I'm, again, bringing this back. Again, this picture holds the fundamental theorem of calculus, and that's why I keep going back to it, because it's a very simple picture. Like I like the basic graphs, and the basicness of it will help us understand the complex theorem later on when we hit it. So again, I'm going to just show you the connections once more. So again, I'm going to shade the area under my rate graph. This is my rate, because speed is a rate. When you have miles per hour, that's a rate. You have different rates in the real world. Like, there's miles per hour, there's gallons per minute, there's different kinds of rates that, you experience. When you experience every day is driving in a car, speed is a rate. So I'm just shading in this area. And let me just change my color. Again, the area under a rate graph, this is a rate. The area of the shaded region, it's 50. The height of the rectangle, it's 50 miles per hour times the base of the rectangle This is my base, 3 hours. When you multiply these two, right? First off, there's some units that are canceling. So this is kind of getting deeper into the specifics. So hours will cancel out when you multiply these two units. When you multiply the rate times the time, you get your remaining unit. In this case, see how that's how we get our distance, which is miles. So when you multiply these out, you get 50 times 3, which is 150 miles. And it isn't a coincidence that this area, the area under the rate graph, is giving you the total distance after 3 hours that you're on the whatever driving or something. Total distance after 3 hours, 150. So again, area under the rate graph gives me total accumulation. Remember, accumulation just means whatever is getting accumulated. In this case, it's distance. Because sometimes the thing that's getting accumulated is not always distance. So that's why we call it total accumulation. And then the other part of it was, but if I find the slope of this, so rise over run, so my rise is 150. I go up by 150 miles, and my run, 3 hours. If I do this division, 150 divided by 3, that gives me 50 miles per hour. And this is my rate, 50, the constant rate, 50 miles per hour. And let me just type out what I just did. When I find the slope of the accumulation graph, I get my rate. Why am I bringing this back? It's important again, and also it's going to lead us into the next Padlet check. And again, it's super important to just make sure we solidify how these two graphs are connected, because it's going to relate to the fundamental theorem of calculus. So feel free to like take a picture of something on your phone or something if you need to, because I'm going to keep showing this this here back to us throughout this module. Essential question that I had you all think about is, how is sigma notation connected to Riemann sums? We paused here and had you all think about this essential question that we're going to investigate today. And then back to this. So we're going to go ahead and focus on these equations, these representations for the visual of finding the left, right, or midpoint Riemann sums. But I expressed that we're going to only take a look at the left Riemann sum, and that if you want to, as a student, explore the right and the midpoint connections, you are free to do so. Those might show up in the AP exam. But for the sake of hitting our essential question understanding, we're going to focus on the left Riemann sum. Okay, so we started off with re-engaging with what we did on Tuesday, which is we did a left Riemann sum to approximate the area under the curve of our function f of x equals x squared between 1 and 3. So I mentioned that in order to make the connection, we're going to find the patterns that are happening. So I noticed that to get the function heights, there is a pattern. It's the fact that I am taking a subscript input. So for example, as I'm plugging in whatever x sub 0 is into my function to get the output, I'm plugging in whatever x sub 1 is right here, the upper left-hand corner, to get my output, and then so forth. So essentially, the formula breaks down into this. We are finding the rectangle's heights by plugging in f of x sub I. This is representing all of those rectangle heights that you see right here. Because x sub I, the subscript I, is going to represent 0, 1, 2, or 3. So that is a condensed way to represent those heights. Another pattern that we pointed out was the fact that these 0.5s were always being multiplied to our rectangular heights. And those 0.5s, let me draw some arrows to them. Those 0.5s in calculus and in math in general, we call them as delta x, which means change in x. So we have our rectangle heights, we have our rectangle widths. We know that to find the area, to find the area of a rectangle, we multiply these two together to get the area, right? But not only that, we had to add up all of these rectangles to get the area, and that's where sigma's coming in. And we start at 0 because our first subscript input was 0, and our last subscript input was x sub 3 right here. So that's the last upper left-hand corner. That will stop at 3. And then here goes our formula, which is base times height of the rectangle. This right here is a condensed way to represent all the work you see here. And I also simplified that. I simplified that to be everything else the same except for the fact I replaced the delta x with the 0.5 because that was the common width of all the rectangles in this particular problem. There is the connection. So we paused for questions, and there were some questions that came up. But other than that, we went ahead and we processed our understanding of this connection in a Padlet. How is sigma notation related to Riemann sums? A lot of you are making that connection. Amazing. So then we moved on from that, and we kind of did a whole class exploration with this tool. So this was me at the front, and you all were taking a look at me playing around with this tool. So we noticed that the fact that 4 rectangles doesn't really approximate the area under the curve between 1 and 3 of our function really well. It doesn't. So we played around with the number of rectangles under the curve. So when we said, okay, let's try, I think someone suggested 26. So we did 26 rectangles. Take a look. 26 is a pretty good estimate. There is less white space under the curve. And if you scroll down on the tool, you see the sigma representation, and it actually calculates the area for you. So it's saying that it's about 8.36. Then someone else suggested 27. So we did 27. 27 looks very similar to 26 visually, but 27 rectangles is eliminating more white space from under the curve. And then we continue with the trend. So let's try 100. If you look at 100, that looks pretty cool. Until you zoom in though, you see the white spaces are still there. Then I was trying to put another number, but somehow it kind of like went very large. I forgot, I think I put 230 or something. And take a look, it almost looks like a solid fill-in of that area under the curve. Except you do, if you scroll it, if you keep zooming in, you're gonna see white space. Ultimately, we even did 1,000. And take a look at the area estimate, about 8.66. If you round it, again, this looks fully filled in. And if you zoom in, it's going to be hard. Like, whoa, where's the white space? But eventually you'll see it. You'll see some white space right here. So we went ahead and from this investigation as a whole class, we jumped back into the Padlet on column number 8. And I asked, how many rectangles would you say that we need to get the perfect area? We were on the right track because we all chose large rectangle numbers to represent that sum. I highlighted that a few comments, the fact that the bigger the number, the less the white there'll be, because that's going to lead us into our big idea. I also pointed out another one that says, I would say NA because there's always going to be space under. So how can we get the perfect area? So I really highlighted this comment. And then again, there's that comment again, less white space of an estimate. You'll get more correct if you use more rectangles. That actually is highlighting the idea, the fact that the more rectangles is indeed better approximation. What does that mean? Let's make some connections. So we're gonna make connections to this integral symbol. So far, y'all have seen this integral symbol as meaning antiderivative, but we're going to now connect this symbol to area under curve. So that is actually the mind blow moment. So we have right here a left integral with its sigma notation representation. So we've seen this already. Now we're going to transition into the better estimate, the fact that the more rectangles equals better. was what was made as the connection, even in the Padlet, right? So I went ahead and rewrote the sigma representation of the left Riemann sum. But if we want as many rectangles as possible, guess what, y'all? We're gonna bring back limits. Let us make sure that we have the limit for the number of amount of rectangles go to infinity. So we have more and more rectangles. So this top number n is going to infinity. And when we have this, guess what, y'all? And then there's a little written description of what I just said. When we have an infinite amount of rectangles, everyone, that is the integral. So it's wild, right? So there is a connection to integral and antiderivative, which we will continue to explore. But now we have made a connection with this symbol and area under curve. This is going to give us the perfect area under the curve because we use the limit. So that was huge. That is a huge, big idea. And we then, and I put seriously because that's huge. And then we jumped into an application of the problem. So let's say on your homework, you see this. Find the integral from 0 to 2 of this function x dx equals. So step 1, I said, is you should graph this function on Desmos. How I inputted it was y equals x. And because we know that this symbol means find exact area under the curve, let's go ahead and find the exact area under the curve from 0 to 2. Oops, because that's what it's saying, from 0 to 2. And let me change my color. But from 0 to 2, the area under the curve, y'all, it's going to look like a familiar shape that you know. By the way, y'all notice how when we say area under the curve in math, we stop at the x-axis. We don't go below it, like when it's like this. So I'm just shading in this area. And when I shade it in this area, y'all recognize this as something familiar. It's a triangle, basically. So we are able to find the exact area under this curve using geometry, actually. So I'm going to go ahead and share with you the ideas that was expressed by our very own students. An idea was, what if we imagine or envision this being a very large square? To find the area of a square, I know that the length is 2, the height is 2. So I would just do 2 times 2, which is 4. But because this is a triangle, we divide it by 2. So that was the solution that was offered by a student. And basically, we're able to evaluate this integral, and we get 2. 2 is the area under the curve. Like, we don't have any units for this problem, so we just write 2. So that is how we went through this lesson, everyone. Sorry for not recording. I hope you find this helpful. Yep. To the antiderivative, because originally we saw that symbol being used to represent antiderivative. So that's something I want you to think about before we get started with our lesson on the integral. So think about it for a moment and then I'll move us on. I am on slide 5. And then there's some steps there. I see you find the area between 0 and 4. The space is 4 times 4. So then you would multiply and divide it by 2 due to it being a triangle. The area would be 8 units squared. We have 8 question mark, 8. We got another 8 coming up. And then a few of us are still working. So let me go ahead and give y'all time, my bad, for you to fully go ahead and enter in your work for this. Because I know we have 1, 2, 3, 4, 5. I see 5 answers. So let me go ahead and wait a bit. My bad, y'all. All right, I'm gonna go ahead and bring us back here, y'all. So the answer for this problem is indeed 8. I do see it reoccurring here. So if you did not get 8, take a look at either you see some algebraic steps or you also see some verbal explanations. See, I like that. See how there's Grigory has like the mathematical steps written out nice and clean. Then we have Sophie on here. Write out the steps verbally. I also like this too. Take a look at this kind of train of thinking down here. Sophia K. So awesome. Okay, so it looks like we're in general agreement though, what I'm seeing here as far as our answers are concerned. Awesome. Function X, when we found that area, was 2. Then we moved on and said, okay, what about 0 to 3? We went ahead and found the area. Y'all found it was 9/2, aka 4.5. That was the second one. Third one, right now we just did the area from 0 to 4 of this function X, and we found it was 8. The question I have for you to enter into this box for your first participation on the Desmos is, are there any patterns that you notice? That's our question today. Are there any patterns that you notice? Go ahead and enter that here. All right, everyone, I gotta bring us back. So take a look at what y'all have here. So what's gonna happen, everyone, let me stop my share, is we're gonna continue and finish this tomorrow, and it will be for grade. So jump on in tomorrow. Y'all have a sub. Let me know how it goes. I do not know how Zoom subs are gonna go. Let me know. Let's wish for the best.